What I'm going to show here is a real world example of how this cognitive drift is going to express itself, in this case, in a C++ program. And I'm going to show you partial implementations of this code as sort of explain this. It's a little bit hairy here, so you're going to have to stick with me. So I have this parser. And we have this parse own method, and you can see the documentation here that it's going to return this standard variant of either the data or some sort of error message that indicates that something failed. So given a character buffer and a length, that's how this parse is defined, it is going to return this data owned structure. Now, because it's a variant, we have to disassemble that. So here I'm using this holds alternative method to make sure that the variant that's returned by parse owned is the actual data owned structure, that the parse happened successfully. So the if check here is sort of the C++ way of unwrapping an optional or a result variant type. And assuming that it parses okay, and all of my examples here do parse okay, but I include all of the guard code as well, we're going to get that data owned struct, or really a reference to that struct, from the variant that's returned, and I make sure that the name value on the data is the string hello world. So this is the simple code that is being used, and we're going to look at the evolution of both the parsing code and the use of the parsing code, how we pass and maintain the buffers that are passed to it over time, or really over time and space, if these are, say, different teams or even different people or the same person over a different period of time. Looking at the data owned structure that's returned, it is simply a standard string. So it's going to make a copy of the data that is passed into it and return an owned copy of it. It has no reference to the original data that was passed into it. Now, the actual implementation of parse owned doesn't really matter, but I'm just doing some simple error checking here. I'm going through the length of the buffer that is passed into it, looking to make sure that every character in that is an ASCII character. If not, I'm going to return that error in the error variant side of it. Assuming that passes, we're going to create our result type, assign the buffer or make a copy of the character buffer that's passed into it, and we're going to return the result. Very simple and straightforward. Now, my use of this in my application is going to evolve over time. And we're starting off with really a copy of what we had in the test, where we have this hello world. This is now sort of allocated statically at compile time. We call parsed. We do our if guard to see if it holds that, and we are going to print out the value that's stored in here. And this is just the basic use of this. This is always going to work. In fact, the parse owned version of this will always work because it's always going to be making a copy of that data. And this making a copy of the data is going to be sort of problematic because over time, this is conceptually going to be a bottleneck in our program. And we want to be able to avoid that copy, either because we don't want the extra allocation of memory at runtime, or we're looking to eke out more speed because this is becoming a bottleneck in our program. So this is going to evolve over time, and we're going to look at that evolution that will cause breakages in this that is really undetectable from the point of view of that we don't, that we have this cognitive drift. Now, in this sort of analysis, I'm making this sort of following claim that given this cognitive drift, the idea that our understanding of different parts of the code is going to vary over time, um, one of these following things must be true for any sort of modifications, feature additions, or maintenance or improvements. These have to be true for it to be correct. And one is that the developer just gets lucky, doesn't break anything. And you're rolling the dice at that point. The second one is that they already have a deep understanding of the parser and the buffer interaction, but we've kind of already said that this cognitive drift, even for a single developer, is not necessarily true. And the third one is that the developer has read and understand the documentation for both the buffer and the parser, that they understand the interaction between the buffer and the parser with respect to, say, lifetimes and ownership, and that this documentation is going to be current and complete and correct. And that's really challenging. And that's where in the previous video where we put in process, either standards or discipline, to try to make sure that this documentation is correct. But this is a sort of a pretty hard pill to be able to swallow. And we'll be able to solve this really with the safeguards that newer generation languages are going to bring to the table. So in this hypothetical but very realistic example, time passes and this is a bottleneck in our program. It's a problem. Maybe we've gone up in the DAO levels and we can't allocate memory. Maybe we don't want to allocate memory for whatever reason. Somebody comes along and says, "Hey, I can make this 10 times faster by not making a copy of the string and referencing the original data that we have passed in." So this person creates this data shared, and in reality, they might rename data owned to data shared, or they're going to be implementing this directly into data owned, but it migrates. The point is that the development migrates to the shared data representation of this, where we're going to point inside the buffer because the buffer already contains data in the shape that we want. So we're just going to point to it rather than make a copy of it. And in this case, I've commented out the string view just to use a const char to make it a little bit more clear. If you were to be more C++ like, you would use a string view, but internally they're really the same thing. They're just referencing memory that it doesn't own. And the parsing code is not much different than before, except we're going to make sure that the very last byte in our buffer is null terminated, and we're going to set the name field directly to that buffer rather than using a standard string to make a copy of it. Now, our use of parse shared doesn't actually change much. In this example here, I'm using a standard string as a buffer to sort of hold that because I want in future implementations to be able to drop that. But instead of calling parse owned, we're calling parse shared. It's the same API. This would be a drop-in replacement if you were to just change the data types being returned, and this works because at the point of usage here, the original buffer still exists. Everything's okay, and everything's great. People are happy. It's working 10 times better. We cash in. This is great. Patting each other on the back. We get awards, another piece of glass on your desk, everything like that. But just wait, because there's going to be a problem, because the person doing this says, "Hey, we can do some double buffering and share, or we don't want to allocate a buffer each time and keep that around. We're going to be loosey-goosey with our buffers because that's now a bottleneck in our program. We're going to modify the network stream so that we're getting buffers and maintaining maybe a buffer pool, something like that, obvious sorts of improvements to the software as you go from a sort of development prototype environment into a production environment. So our use of the buffers start to change. And in this case, I'm using the parse owned version. So at the point of calling, this is making a copy of all of the data. So when we modify our buffer sort of out of band, the original buffer that was passed in, we're not modifying the parsed one here because we're using parsed owned. We're not using the parse shared. And so this modification of buffer doesn't affect what we've parsed. So this actually works just fine. There's no memory corruption. There's no conflict of data. Everything is copacetic. But if we were to be using the shared version like this, we're now in a world of hurt. Well, we're starting to expose where the issues are, because here we are referring to the same original buffer. So parsed here has a pointer to the original buffer data. So when we modify it here and change the first character to a J, or even worse, if we were to be loading this in from another thread, from another system, it containing the next data packet, or even worse, containing a partial data packet, we're going to be modifying this midstream. So at the point that we are printing out this data, this is a problem because it does not refer to the original data that we had. It is maybe, if you're lucky, you're going to catch this as an application sort of behavior that is not getting the right data sometimes, a tricky sort of thing to discover. We haven't yet hit the point of something causing a crash, potential crash, but we're really, really, really close. So here we've hit the point of being a problem. This is going to cause corruption, undefined behavior, crash. Something is going to go wrong that may not actually exhibit itself as a crash. You're not going to know. Because in this case, we're doing the same thing. We're parsing the shared buffer. Everything's cool here, except we are now assigning our string to something new. In this case, a string that is considerably longer than our original string. And in my implementation of the standard string library, the original buffer that was stored for Hello World was 15 characters. And this is longer than that. So when we assign this new buffer, it will free the old buffer. Freeze the old buffer. That should streak terror in your hearts. And we'll allocate a new buffer to hold the rest of this data that we have here. So we now have a dangling pointer issue. And when we print out what's here, it is really unknown what's going to happen when we try to print out something here. This is going to cause problems. It actually doesn't crash on my system because the process still owns that unreferenced data type, or that data buffer. It's not always the case. Depends on how it's compiled. It is a ticking time bomb because this is undefined behavior. And this version here does really kind of the same thing, except we are completely deallocating that original buffer. We don't potentially have another character string in place. Again, we have an absolute dangling pointer issue here that is completely unchecked by the compiler and will cause a problem. And the real issue is, like, this causes a problem, but there is other usages of this that don't. And this is where that proper documentation, proper communication says, oh, if we have all of that, all of these problems sort of go away. But that documentation is challenging to have complete, accurate, and so on. So we want to then layer on top of this technology, newer language technologies that properly handle lifetimes, properly handle ownership. And that is going to be the benefit of Rust, because this really contrived but very, very realistic example is reality in software development, and happens over and over and over again, and exists in the software that's out there right now that you don't know about. So this is already 15 minutes. I'm going to just push through. This is going to be a long video, and good for you if you make it to the end of this. But we're going to look at the Rust implementation of this as well, and show you how the compiler is stopping you from doing things like this. Oh, before I go to that, just to show you the output of this. At this point, this is the one where we overwrote the first character, so the data that was parsed didn't point to the original one. This is the one where we changed the buffer to the quick brown fox jumped on a lazy dog, and the original buffer got weirdly corrupted. I don't know what the compiler did under the hood, but it was able to print this out, but it was pointing to bogus data. This last one, this is where I deallocated the buffer. I freed it directly from the unique pointer that was there. I reset it, cleared the buffer, but it still print out the original data. So that was still in memory somewhere, but unreferenced, at least at the point in time that this got accessed. So it was able to print out the right value, but just got by this by it was lucky that it worked at all. Okay, so this is our full Rust implementation of the same thing. We have the two data structs, data owned, which has an owned version of name represented by a string. So it's going to own a copy of that, and the string is going to be allocated on the heap. And we also have a shared version of that is keeping a reference to the original name. And we have to use the lifetime references to indicate that this structure, or really data inside of this structure, is going to refer to something, and that the struct that is going to be created must have some lifetime representations that are going to be maintained by the compiler. So there's some additional annotations that are required by the compiler to let the compiler know that there is going to be a lifetime reference in here. And it already knows that, but it's forcing you to declare that. The parser, I want to make clear that this is not an optional sort of thing that you're doing. Like if you were to be using shared pointers or other sort of newer semantics in C++ to try to manage the ownership. This is a required thing that is going to be dealt with at compile time. The two parse methods are just going to create a string from a UTF-8, or it's going to create a string reference from a UTF-8 and return the value. And I'm explicitly stating here that this data shared is going to be referencing this. I could actually take this off, but it's useful from the communication point of view that when there are error messages, this sort of helps the user know what went wrong. Now, here's our use of this. And this is, I'm going to have asserts in here just to be able to show that this works. And if I were to run this, all these asserts would hold true. So if we have, well, let me show you what the types are here. The hello world stir is a string reference, and we get sort of the byte representation of what that string is, that we can use to pass into the various parsing functions. So parse owned here is going to return a data owned, and I'm using the question mark operator to deal with the error handling and unwrapping. in a convenient way. And in this case, we do parse owned and we parse zero copy, and all of these work just as expected. And because the original buffer still has a lifetime that is going to be available here, everything is okay. To sort of hint at where we're going here, I'm going to change the original array, and we're going to make a copy of that, and we're going to turn that into a vec buffer here. So vec buffer here is going to be a vec of u8. It's allocated on the heap. This allows me to drop it or free it so that I can demonstrate that the compiler is going to get really angry with you if you are going to lose a reference to the original data. In this case, nothing has changed because our parsing for both the owned and the zero copy still has a lifetime reference to that original data buffer. So this buffer exists and it is okay. This parse zero copy is going to work just fine. So here's where things start to go wrong. In this first version here, I'm using parse owned, and I'm doing this inside of a block. So vec buffer here, once it falls out of this block and sort of returns the data owned out of into this, this is definitely a Rust-like way of doing things. This is okay because parse owned is making a copy of the original buffer. So even though the vec buffer is going to be dropped at the end of this block, since we made a copy of the string, this first block works okay. The next one I have commented out here because right now it's uncompilable. So if I take this out and let the analyzer say what's wrong with this, we're going to have this issue here that says vec buffer does not live long enough. The borrowed value does not live long enough. It's dropped here while it's still being borrowed. It binds to it here, and it's later tried to be used here. So the compiler knows that parse zero copy is going to return a data structure that is going to refer to the original buffer, telling the compiler that this data shared must, the buffer passed in must live at least as long as the data shared is going to live. And because it doesn't, because the reference that we pass in is stored in here and this is going to drop, this is failing. The compiler is going to say, you cannot do this, and it's going to stop at compile time. And that is really the best part of memory safety for Rust, that we are able to catch this at compile time. So mostly for completeness, I have the version where we're changing the buffer out from under it at compile or at runtime. So in this case here, this is the point where we're changing the first character of the buffer, like if we were reusing the buffer for another network read or a file read, and we might be overriding that original buffer. The parse owned is just fine. This is very happy. There's no issue with that, and it's going to work correctly. The behavior is what we expect, and there's going to be no compile or runtime issues. But this one here, I do the same thing, and I have the modification inside of a block just so I can configure it out. But we're doing the same thing here where we do parse zero copy, where we get a parsed version of that, and then we try to change the original buffer, just like we did up above. And this is going to fail. Well, it's not going to fail. It's going to have a compile time error. The compile time error is actually not as friendly as before. It says that we can't borrow as mutable because it's also borrowed as immutable. That doesn't quite make sense. I mean, it's correct, but the real issue is that there is something that is holding an immutable reference to it. So when we need to change that or do this operation to try to modify it, it's going to fail because parsed is referring to the original data. And because of the ownership rules and because of the lifetime rules, well, not really the lifetime, but the ownership rules says that you cannot do this. So again, at compile time, this is protecting us from modifying that original buffer out from under something that we've already parsed that expects that original buffer to be immutable. And that is memory safety. And it's memory safety at compile time. And that is what is going to save you money. That is the return on investment for memory safety in Rust. And this, again, this is a contrived example just to show you the possibilities. It is simple, and this holds true for even the most complex interaction, especially across threads. So as you go multi-threaded, these same rules still hold. This is game changing. Like, this is revolutionary in the ability to create, deliver, and maintain software that is going to work all the time, and you know that it's not going to have any unforeseen issues because of issues like this, which is quite honestly the largest source of memory corruption issues in software today. So this is a long video. I apologize. Hopefully, you made it through it and you've gotten to this point. I hate it that 26 minutes into this is where you start to sort of understand from a technical point of view where the return on investment is. Need to be able to unfold this so that you don't have to go through this example. But this example is real, and this is what is really going to convince you as a technologist that this is a worthwhile investment to make for learning it and for delivering your products with it. So that's my video. Have a great day. Hopefully you've learned something, and keep coding or something. I don't know. I need a better tagline for ending this, but peace.